So welcome back, students. We want to look at the nature and also the analysis of a graph which would plot of the stopping voltage against the frequency. Again, I remind you that this voltage absorbs the kinetic energy of the electrons. The graph would generally give us a straight line graph with a positive gradient. And if we were to extrapolate the graph, you notice that it will cut the frequency axis at a point and it cuts the voltage axis at a negative value. You can see it's below the zero mark. It cuts it at a negative value. The equation that gives us this graph, remember, is the energy of the radiation, HF, equals to the work function plus the kinetic energy. Therefore, we have HF equals to work function is H times threshold frequency plus the kinetic energy, a half mass of the electron times the velocity of the electrons squared. Now we bring in the situation where the stopping voltage is used to stop the kinetic energy. Remember, we said we can express energy in terms of EVs. That means that if we have used 2 volts, then the energy used is 2 EV, and we can now convert this to energy in joules by simply multiplying the voltage by the electron charge, 1.6 times 10 to power negative 19. Therefore, the stopping voltage absorbs this kinetic energy. Therefore, the voltage we get, then that energy will be in EV. So we can simply talk of the kinetic energy equals to EV. Replacing that in our equation, we'll be having HF, the energy of the radiation, equals to the work function plus the kinetic energy, which is EV. Now, I go back to the graph now. Because it's a straight line, then it will obey the general equation of a straight line, which is y equals to mx plus c. Then we check, what have we plotted in the y-axis? It's the stopping voltage. That is the V. This is what should go to the y-axis. What have we plotted in the x-axis? It is the frequency of the radiation. So we are going to rearrange this equation to obey or in this form. Therefore, I need to leave the quantity in the y-axis on its own. So I'll we first subtract the work function on both sides. Then we'll be having EV equals to the energy of the radiation HF minus H, that is, yes, minus HF naught, the work function. Therefore, we'll have V equals to, that is EV equals to HF minus HF naught. We still want to have this on its own, so we divide through by E, so that we'll be having V equals to, we are dividing this by E, the electron charge, so that we'll be having V equals to HF over E minus HF naught over E, which will give us V equals to H over E F minus HF naught is work function, so that will be W naught, the work function, over E. And now we've left the equation in the form of Y equals to mx plus c. You can see this is what we have plotted in the y-axis, the stopping voltage. That is what we have plotted in the x-axis, the frequency of the radiation. That leaves us with the gradient. Look at the gradient. M, which is the gradient, will be h over E. This is the gradient. The gradient equals to h over E. And therefore, we can use this graph to determine the Planck's constant. The Planck's constant divided by the electron charge is giving us the gradient. That means that Planck's constant will simply be the gradient times the electron charge. Look at a point where now we are at the C, the intercept, the y-intercept. The y-intercept will give us the negative of the work function over E. That means that C, which is the y-intercept, will be equal to minus W naught over E. That means the y-intercept again can give us the work function. Let's take for example that this value here is -2. Remember, we'll get this as -2 volts. The units are in voltage. Therefore, it would read minus work function over E equals to -2 volts. When we divide both sides by -1, then we'll be left with work function. Then we multiply both sides by E. Work function will be 2 EV. Therefore, the y-intercept gives us the negative of the work function over E in EVs. The gradient gives us h over E. Looking at this graph, another quantity that we can use is the x-intercept. Please note that all these frequencies here, the energy or the voltage we are using to stop them is negative. That means we already don't have any electrons to stop. All these frequencies here are not causing any photoelectric effect. At this point, we get photoelectric effect, but the kinetic energy to be stopped is zero. That is why we are using zero voltage to stop that kinetic energy. So this is the frequency that is just enough to cause photoelectric effect. Therefore, from this, the intercept of the frequency axis gives us the threshold frequency. In this case, here, the x-intercept will give us the threshold frequency. So again, another quantity is the x-intercept. The x-intercept, and allow me also to call it the frequency intercept. The x-intercept or the frequency intercept. This will give us the threshold frequency. The threshold frequency. So from this graph, we can get all these quantities. First, the Planck's constant, which you're getting from the gradient, h over E. We go ahead to get the Planck constant. It will be gradient times the electron charge. Then y-intercept, it gives us the work function. And you can see simply, if I read the intercept and it is -3, then the work function is -3 electron volts. If it is negative 4, then the work function is negative, that is 4 electron volts, which we can go ahead to convert to energy in joules. Then from there, we have the intercept, the x-intercept, or the graph where it cuts the axis with the frequency. The value there gives us the threshold frequency. I want you to note, if I had a graph, maybe a situation where I would draw the graph, but we don't have the axis to get the x-intercept, we'll still get the work function, because work function is Planck's constant times threshold frequency. In this case, we will read the threshold frequency from the intercept of the frequency axis. Then we will use the gradient to get the Planck's constant, and we'll go ahead to work out the work function. So join me in the next session as we look at an example on the analysis of the graph of stopping voltage against frequency. We'll also look at a situation where instead of plotting against frequency, we plot against the reciprocal of wavelength. Thank you. Have a nice time.